We will discuss electric propulsion machine. Mainly, we will discuss about the DC machine for propulsion, electric vehicle powertrain, permanent magnet motor drives, surface permanent magnet AC machines, interior permanent magnet AC machine, switch reluctance motor drive, and applications of drives in electric vehicles. DC machine. In early days, DC machine was used widely for various applications. But with the rapid development of power electronics, the reverse-static control of DC motor drive is not used. The DC chopper control is used extensively for DC motor drive. Advantages as smaller size, lightweight, higher efficiency, and it is having better controllability. So DC chopper control is preferred. In basic configuration of DC motor drive, DC to DC converter functions to control the armature current and it controls the output torque of the DC machine. The feedback control variable is the motor speed in the control, while the armature current feedback is mainly for protection purpose. Here we can see the block diagram of the DC machine drive. So it has a DC machine here. It is the DC machine here. Then here is the source given via this DC to DC converter. There is one of the control the voltage and control the power, and it has the sensors for speed and current sensing, and via this controller it is given to control the DC to DC converter. Then the mechanical input will be given to the differential through the fixed gear. This is the gear, differential gear, and it will transmit the power which is in the 90 degrees to the wheels. For electric vehicle propulsion, DC motor drive usually adopts the high-speed machine design to achieve high power density. So as the speed of the machine is increased or it is a high rated, high power density can be achieved. Typically, the machine spins at 5000 RPM and hence fixed gear is incorporated to step down to 1000 RPM for driving the vehicle wheels or as required. So high speed is reduced to low speed using fixed gear and with the wheel speed. In order to provide backward motoring for some application like parking, the DC machine needs to offer reverse rotation, or we can also add a reverse gear to have the reverse rotation. Reverse rotation of DC machine is preferred over reverse gearing, because if you use the reverse gear, the gear will be again incorporated, which can be make the system bulky, inefficient, and overall system will be complex due to addition use of the reverse gear. There are various choices of DC to DC converters and machines depending on the desired operation and performance. Here we can see the structure of a DC machine. The DC machine has a stator on which there is a field winding to produce the magnetic flux. There is a rotor which is placed on the shaft, which is rotating, which has the armature conductors placed on it, which carries the current. So interaction of this flux and this current carrying conductor, it will produce the torque and the motor will rotate. The stator is the field circuit as shown here. Incorporate field winding or permanent magnets also are possible to produce the field excitation, which is the important. The rotor is armature circuit as shown here. Circuit install the armature winding where the armature current is bidirectional and switched by the commutator via carbon brushes. So commutator is there to provide the required conversion say from AC to DC, that is unidirectional torque has to be produced, and that is done by the commutator. Also, it facilitates the collection of the current on the machine. If you see the principle of DC machine, when the machine operates as a motor and the corresponding coil plane aligns with the magnetic field, the force created on each coil can be calculated by F equal to BIL, where B is the magnetic flux density produced by the field circuit in the stator, I is the current, that is the armature current, L is the axial length of the armature coil in the rotor. The developed torque can be expressed as T equal to F into D into cos theta, where D is the diameter of the armature coil or equivalently the rotor angle, equivalent to the rotor, and theta is the angle between the coil plane and the magnetic field. To produce the maximum torque, armature coil should be energized at a position theta equal to 0 degree. In practice, more commutator segments and pairs of carbon brushes are installed to produce continuous and steady torque. So this is the working principle that depends on the flux density, the magnitude of the current, the axial length, and how the coil is energized. Here we can see some common structures of DC machine. The first one is the separately excited DC machine, DC motor, where we can see the field winding F here is excited by separately field supply to get the flux created into the field winding. Similarly, for the armature, that is the rotating part of the motor, supply is given separately via DC source. So that is the separately excited. We can control independently the field current as well as the armature current. Now the next type is here the series DC machine. If you see the field winding now is connected in series with the armature. So how the field winding is connected mainly decides the type of DC machine. If we see here, field is connected in series, so the current flows through the field to the armature. So this is the series type. Now the another is the shunt type. You can see here the field winding is connected parallel to the armature. So both the circuits are parallel, current will flow parallelly because when it is flow from the battery, it will divide here to the armature and another path will be for the field. Next one is the compound. Here it is the combination of series as well as shunt. So you can see here the field is in series with the armature and the whole series field and armature is again shunted by a field winding. So there are a series field as well as a parallel field. So it is a cumulative field and also the flux we can see they are marked with the dots. So current is entering here. Similarly, current is entering. So both the fluxes will assist to each other. So they will sum up or they will add and sufficient flux is created or field flux is created. In the differential compound, the combination is same to the cumulative, but the fluxes are now opposite because we can see the dot one is current is entering at this point and current is leaving. So fluxes are opposite to each other and resultant flux will be lesser, and that is the differential compound. Now one more possible structure of DC machine can be the permanent magnet DC machine, where the field winding which are shown here as series or as a parallel, they are now removed and permanent magnets, you can see here N and S, they are placed on the stator, and it is the structure of permanent magnet DC machine. The same thing are classified here and discussed to separately excited DC machine. Field and armature circuits are separately fed by different voltage sources as shown here VF and VA, and currents are controlled separately. In shunt machine, field and armature circuits are connected in parallel. You can see here and fed by the same source so that their currents are controlled simultaneously. Then we can see DC series machine where field is in series with the armature so that the field and armature currents are the same and controlled at the same time or simultaneously. In cumulative compound DC machine, we can see one connected in series, other connected in parallel. The flux of the series field is in the same direction as that of the shunt field, and they assist each other, so it is a cumulative compound, and resultant flux is addition of the two fluxes. In the differential compound, two field circuits are there. The flux of the series field opposes the flux of the shunt field. That is the differential. There is a difference into the net flux is the difference of the two fluxes. Now the last one is the PM-DC machine. By replacing the winding, PM-DC machine, higher power density, higher efficiency, and sound field compound that is because of this benefits is space saving, winding absent because field winding has and the conductors will have see the permanent magnet DC field excitation in the PM-DC machine cannot attain the operating characteristics with flux control. As the magnets are used, whatever the line, whatever the flux, both the wound field and permanent same fundamental problem. So PM-DC is slightly variable. Permanent magnet DC has also fundamental problem later part, adding the brush, wear and tear. Also there is a sparking. It causes also torque ripples and limits the operating while the carbon brushes are responsible. Then wear and tear here there is a commutative carbon brush. So it may be needs regular maintenance better and therefore DC machines are less reliable and unsuitable maintenance free of limiting their applications modern electric. You see here briefly DC machine Machine can be represented by equivalent circuit, the armature circuit, field circuit, or simply constant flux for permanent. Here we can see armature circuit, field equivalent, that is a field. Here is the field circuit, here is the armature circuit indicating armature resistance, armature, and the supply. Here the field supply and the field inductance and resistance are equivalent, separately excited. Also, the DC machine operation is governed by operations. Here you can see the back EMF flux into omega m, that is the speed. Then armature voltage, E, that is the EMF plus top. Torque is proportional to flux into the field winding current. Field voltage, EF, that is nothing I in the field voltage drop. Then flux is equal proportional field current. Whatever the magnitude of the field, that is the flux, decide magnitude of the field current will decide the flux. For wound field DC machines, flux is generally proportional to the current, which may be independently controlled by the field voltage, depending on armature voltage, depending on the armature current, or dependent on both armature voltage for the separately excited shunt series or compound. So whenever wound field is there, it can be controlled. In contrast, flux is essentially uncontrollable for permanent magnet DC machines. Without external control, the torque speed characteristics of DC machines can be readily obtained. So here we can see the characteristics of DC series motor. First one is the torque versus armature current. Another is the speed versus armature current. And last one is the speed and torque characteristics. Now, as we increase the armature current, you can see here the torque, armature torque will increase proportionately for the DC series motor. And this is the shaft torque. After allowing certain losses, there will be a shaft torque PSH. Now, the next characteristic is armature current. As we increase the armature current, you can see the speed go on increasing. Correspondingly, there is a rise into the torque. So speed and torque, they are inversely related. This is the characteristics of DC series motor. Now characteristics of DC shunt motor. So here we can see armature torque and armature current. It is the linear characteristics. It is a proportional characteristics. As we increase the armature current, it increases the torque linear. Here the speed armature current. Now as DC shunt motor, the field is parallel. The speed is almost constant, and practically it is having slightly dropping nature. So overall speed and torque characteristics is again inversely related. We can see the characteristics of DC compound motor, where it has a cumulative compound field, cumulative compound connection and differential compound connection. Also, if we compare with these other characters, that is series and shunt, this is shunt characteristics, this is a series characteristic, and we can see the cumulative characteristics is at this position, and differential compound is here because in differential compound flux is difference of the two windings flux, that is series and shunt, and here cumulativity is added. Similarly, we can see the characteristics of DC compound, that is the speed and armature current characteristics. So here speed is almost constant for shunt. Then we can see here for series, then cumulative compound and differential compound. Similarly, the torque speed characteristics as discussed for series is inversely proportional, then separately excited shunt permanent magnet machine, then this is the cumulative compound, then it is differential compound. Mostly it indicates that the speed decreases linearly as the torque increases, and the speed regulation depends on the armature circuit resistance. In case of DC series machine, the corresponding torque speed characteristics can be given, that is the torque is proportional to VA square divided by RA plus constant into omega m square. These characteristics indicate the speed is inversely related to the torque. This characteristic is particularly suitable for applications requiring high starting torque and heavy overload. However, it suffers the problem of overspeed when operating at rated voltage under no load or light loads. In case of cumulative compound DC machines, the torque speed characteristics lies between those of the shunt and series machines as seen in the earlier diagram, depending on the relative strength of the shunt and series fields. The corresponding no load behavior mainly depends on the shunt field, while the dropping behavior is given by the series field. The characteristics is attractive for applications requiring high starting torque. At the same time, no load speed can be limited to a safe value. For the differential compound DC machine, the series field reduces the air gap, so it is the difference in the two fluxes when the torque increases, causing the speed to rise in such a way that it can be used to compensate the speed torque due to the armature resistance. On overload, this effect will cause the speed to rise to instability. Thus, the machine is seldom applied to motor drive. So, differential compound is rarely used. Next, we'll see DC motor control. The speed control armature is divided into armature voltage control and flux control, or it is called as a flux weakening control. When the armature voltage of the DC motor is reduced, the armature current reduces and the torque also reduces, thereby decreasing the motor speed. In contrast, when the armature voltage is increased, the motor torque increases, thereby increasing the motor speed. It can be observed that motor can operate for any torque speed characteristics below the natural characteristics. Also, the slope of these characteristics does not change with the speed. Since the maximum allowable armature current remains constant, the armature voltage control has the advantage of retaining the maximum torque capability at all speeds. It is about the armature voltage control. The armature voltage cannot be further increased beyond the rated value if you are controlling by armature voltage. This control is used only when DC motor drive operates below its base speed. So here we can see this is the natural or base speed. Then for constant flux, we are decreasing. At constant flux, we are decreasing voltage, so you can get the speed below the base speed or the rated speed. But here you can see we are keeping constant voltage and decreasing flux, we can go above the natural or rated speed and at higher speeds. Here, the characteristics of DC motor, series motor is shown. Again, we can see this is the natural characteristics. So by controlling the voltage or decreasing the voltage and keeping constant, we can get the speed control below the rated speed value. To get the speed above rated value, we can decrease the flux, keeping the voltage constant. So when the field voltage of DC motor is reduced, weakened, while armature voltage is fixed, the motor back EMF decreases. Because of low armature resistance, the armature current will increase by an amount much larger than decrease in the field. Thus, additional motor torque causes the motor speed to increase. Under flux control or flux weakening control, the torque speed characteristic of the separately excited and series DC motor are given in the graph here. You can see here with the dotted lines. It can be observed that slope of these characteristics no longer kept constant but is affected by the flux. In order to achieve wide range of speed control, the armature voltage control and flux weakening control should be independent, which can only be applied to a separately excited DC motor drive very easily. Below the base speed, the armature voltage is varied, whereas flux is kept at the rated value. Since the maximum allowable armature current is constant, the torque capability under armature voltage control can be kept constant, so called the constant torque region. Above the base speed, the flux is reduced or weakened, whereas the armature voltage is kept at the rated value. Since the armature voltage is fixed and the maximum allowable armature current is constant, the back EMF remains constant for all speeds. Hence, power capability is constant, so-called constant power region. So you can see here the constant torque, and here you can see the constant power where the torque is reducing. So there are two regions. Armature voltage control will give the constant torque, and flux weakening control gives the constant power region. The regenerative braking. Regenerative braking is exclusively adopted by electrical vehicles because of the corresponding battery pack has the ability to absorb and store the mechanical braking energy. So during braking, when we apply the brake, so electrical braking can be applied and energy generated by the machine as a motor can be stored back into the battery. The rheostatic braking and plugging are seldom used in electrical vehicles since the corresponding braking energy is wasted in resistance. So it is better to use the regenerative braking rather than rheostatic braking or plugging. If DC motor is fed by fixed voltage source, the regenerative braking can be performed only for speeds above the rated speed. So speed has to be above the rated, then it is possible to get the regeneration when fixed voltage source is there. With the use of DC chopper, it is possible to obtain regenerative braking at lowest speed. So it is based on the two quadrant DC chopper. The armature terminal voltage can be controlled by tuning the duty cycle to be lower than the back EMF E so that the armature current becomes negative, hence creating negative torque for regenerative braking. Here we can see the regenerative braking of separately excited DC motor drive. So this is the natural speed or rated speed, and this is the below rated, and this is the above rated speed. For the separately excited DC motor drive, the torque expression for regenerative braking is the same as that of the motoring but with negative value. Also, when desiring regenerative braking above the rated speed, the flux need to reduced accordingly. So this is what is required during the control. Now applications of DC motor drives in electric vehicle. We'll see some application examples. All types of DC motor drives, that is separately excited DC, series DC, shunt DC, and PM-DC machines have been earlier used or they are applied for electric vehicles. Among them, separately excited DC and series DC motor drives are widely used for electric vehicle applications. First certified AV complying with Federal Motor Vehicle Safety Standards for line production in North America commenced in 1990. Electric Z van, as shown in this figure, adopted separately excited DC motor, provides a rated power of 45 kW and torque of 323 Newton meter. The transmission was fixed gearing, forwarded and reverse having ratios of 1.85:1. The vehicle top speed was 88 km per hour, installed with a safety nickel cadmium battery pack of about 40 kWh, run 96 km at a weight of 3,538 kg under the J22-7A-C driving cycle. The battery pack was charged by an onboard charger, which took 8 hours for full charge. The second application, the Fiat Pan Electra, is the representative EV that is used the series DC motor drive. It was used in 1990, launched in 1990, one of the first mass-produced electric vehicle model using series DC motor. It could provide the rated power of 9.2 kW at 2,500 RPM. It was equipped with 4-speed transmission, which could offer a top speed of 70 km per hour. To accommodate the lead acid battery pack of about 90 kWh, it only had 2 seats and the range per charge was 77 km. The battery pack was 350 kg with a charging time of 8 hours. This is about the Fiat Panda Electra EV. An important milestone, the third application, is the electric vehicle lunar roving vehicle LRV. It was one of the milestones in the use of DC motor drives for vehicle applications. So this LRV was to operate the low gravity vacuum environment, the Moon Apollo lunar missions. LRV had a mass of 210 kg with a payload of 490 kg. The wheels were driven by 4 series DC motors. Input voltage was 36 volt to output the rated power of 745 watts and speed up to 10,000 RPM via individual 80:1 harmonic drives. The corresponding speed control was handled by using PWM DC chopper. Installed with 236 volt silver zinc potassium hydroxide non-rechargeable battery with capacity 121 ampere. It offers a range of 92 km. By using front and rear steering motors, which were also series DC motor rated at 75 watt, LRV could offer excellent maneuverability, the quality of moving freely. Overall cost was high, that is 38 million US dollar. It was first used in the Apollo 15 mission in 1971. This is the lunar roving vehicle using series DC motor.